Hello, everyone. Welcome to Astronomy on Tap. I am Dr. Cameron Hummels. I will be your MC and one of the speakers for this evening to a special Astronomy on Tap for Star Wars and Star Trek fans. We're going to talk about the science behind some of these science fiction universes that you may be familiar with from popular media in the last 50 years, I suppose. A couple of quick announcements before we get moving. So the schedule for tonight, after I finish with these announcements in the next couple of minutes, I will be joined by Dr. Michael Wong, a postdoctoral fellow at the Carnegie Institute who works on exoplanets and astrobiology. And he is going to give a presentation about 25 minutes on the science of Star Trek. And then we'll take some questions from the audience through whatever medium you're watching this on right now. So if you're on YouTube with the comments or Facebook with the comments, ask your questions there, and I'll be monitoring them and be able to ask Mike those questions for you, and then he can respond. So we'll do Q&A for about 10 minutes after his 25 or so minute talk, and then I'll introduce me. Because I'm the other speaker. I'm going to talk about the science of explore Tatooine here, the science of Star Wars, and again, that'll be, I don't know how long that presentation is going to be. I haven't really practiced it yet, so hopefully it's passable and interesting for people. And then we'll take questions for me as well from all of you guys. And then we'll have some conversation and just discussion about science fiction and these various science fiction universes, and then we'll do some pub trivia after that, where you guys are all encouraged to answer some of our questions for all of you, and there's an interactive way in which you can answer those questions, and we see the responses and so on and so forth. So so stay tuned for that. So all in all, this will take somewhere on the order of an hour and a half or 2 hours, but feel free to come and go as you please, or if you're watching this after it's been recorded, to zip past the boring stuff, whatever you consider to be the boring stuff. But I promise there's going to be some pretty awesome stuff, so don't skip too much. And yeah, so we do these Astronomy on Taps once a month. Traditionally, they were held in a bar. Now they're on YouTube. I'm trying to get us back to doing it in person again. It may be as soon as next month. Stay tuned. I will keep the announcements coming. We have a sister series of events called the Stargazing Lectures through Caltech Astronomy. Those happen one Friday night a month. Our next one of those is given June 3rd, which is not very far off. It's only a couple weeks from now. And it will be given by Dr. Janos Dewberry, talking about planet quakes, not just around our Earth, but being able to probe with seismic activity the interiors of some of the gas giants like Saturn and Jupiter, and what their interior structures are and what implications that has for their interactions with their ring systems and their satellites and so on and so forth. So that should be super cool. That will be both in person at Caltech as well as streamed online, and hopefully we'll get the microphone problems that we had last time sorted out, so it won't be it'll be a better sound quality than we had. I'm trying to think if there are any other announcements. I think that's basically it. We will host an in-person Astronomy on Tap in June in Bishop, California. If you happen to be in the Eastern Sierra, we will be hosting one at the Mountain Rambler Brewery at the end of June. I forget the date, but I'll post it here. I'm not sure if that's going to be live streamed or not. And then we'll start doing our foreign language ones again as well. We have a Spanish one and a Mandarin one, but those will primarily be over Zoom, but you'll see the announcements on here. So anyway, enough announcements. Hey, Mike, you wanna jump in here? How's it going?
Hello. Hi. It's going really well. I'm so happy to be back at Caltech, I guess, virtually for one of these outreach events. Can you believe it's been 5 years since I did one of these?
I know, it's pretty wild. It's pretty wild.
Yeah.
Yeah. So everyone, Mike was a graduate student here at Caltech in the Planetary Sciences Department. He finished his PhD in 2018.
Yeah.
And then you went you went to University of Washington for a postdoc, right?
Yep, I was there for 3 years.
Okay. And now are you still there, or where are you now?
I'm at the Carnegie Institution for Science at the Earth and Planets Laboratory in Washington, D.C.
Awesome. Awesome. Is it great? Is it a good place?
It's amazing. I love it. Yeah, it's a wonderful place to be.
Sweet. Cool. Yeah. And zero pressure. I don't actually even know if you're drinking. I'm drinking. I was trying to find the most astronomy themed beer. So I have the Sky Kraken from
Nice.
Seattle-based brewery, Fremont, which I'm pretty happy about. I couldn't find any Star Wars beers.
Oh, what do you have? I've got my Romulan ale.
Oh, that's
it's just blue Gatorade.
Okay. Yeah, and so, well, I guess a couple of quick disclaimers. Neither Michael nor I are affiliated with Disney or Paramount or Lucasfilm or Roddenberry Estate or anything like that. We are science. Yeah, well, yeah. If you want to change that, if an audience member wants to change that, we are scientists, and we are talking about the science of these things. Even though we're both fans of these science fiction kind of universes, we're not affiliated with them. So hopefully we'll be able to add some information, some realistic information to your understanding of how to interpret these worlds and how to enjoy these worlds. But yeah, this is not an official like Disney publication or anything like that. Yeah. Do you want to start us off?
Sure.
Sweet.
Might as well get going.
Oh, and the other thing is, I like Star Trek. I'm a bigger fan of Star Wars, but I think that's just because I was introduced to it first at a younger age. But this is by all means not meant to be an antagonistic thing. Like, this isn't like, oh, Star Trek versus Star Wars kind of battle. This is just like, let's talk about science and let's talk about science fiction. So
yeah, I mean, my dirty little secret is that I love Star Wars so much too. Just not quite as much as Star Trek, but it's one of my top fandoms, up there with Lord of the Rings and Harry Potter and things like that. So yeah, Star Wars is so awesome. Yeah.
Awesome.
Okay.
Cool. Okay. Do you want to go ahead and share your screen?
Yeah, let's do it. All right. Can you see that?
I can see it. It looks great. And my introduction for you is Dr. Michael L. Wong is a planetary scientist and an astrobiologist at the Carnegie Institute for Science's Earth and Planets Laboratory. Mike studies biosignatures, planetary habitability, and the origins of life. In his spare time, he hosts Strange New Worlds, a science and Star Trek podcast. Now, that's different than the Strange New Worlds television program, correct?
Correct. The television program is the live action version of my podcast that Paramount decided to make after they heard me speak. No, just kidding. It's it's a completely different show called Star Trek Strange New Worlds, and I'm really enjoying it.
Sweet. Okay, cool. Well, I'll let you take it from there, and we'll talk more about your podcast afterwards.
Sounds good. All right. Welcome, everyone, to the science of Star Trek. So I always love to start these talks off with something you may have heard of called Faraday's law of induction. You may even have played around with it in science class. Generally, it's demonstrated with a coil of wire and a magnet, and you pass the magnet through the coil of wire, and the changing magnetic fields induces an electric current in the wire. When this was discovered, it helped us unify the forces of electricity and magnetism into something that we now know and love as electromagnetism. Now, imagine that you could somehow unite the forces of electromagnetism with the force of gravity. And as Einstein told us, gravity is nothing more than the bending and rippling of space-time. So what if you had an electromagnetic energy source so powerful that you could literally warp the space around you, expand it behind you, contract it in front of you through the power of science, plus a little sprinkling of imagination? You will have created a tidal wave of space-time that you could surf faster than the speed of light. What would you do with such a marvelous engine? I think I know. I think you would venture out into space the final frontier. Explore strange new worlds. Seek out new life and new civilizations. Boldly find yourself under a pile of tribbles. You'd be an explorer, going where no one has gone before, and all the while making new friends, sharing fond memories, and learning what it means to be human. This was the vision of a man named Gene Roddenberry, who in 1964 wrote a proposal to NBC Studios for the creation of a brand new television show that he called Star Trek. Now, ever since Star Trek's inception, Gene Roddenberry knew that he wanted science to be at its core, so much so that he wrote in this 1964 proposal about an equation penned just a few years earlier by astrophysicist Frank Drake. Now, this is what Drake's equation looks like. It's an attempt to organize our knowledge and our ignorance about the cosmos to estimate the number of intelligent transmitting civilizations in the galaxy. Thing is, back in 1964, you couldn't just Google Drake's equation, right? In fact, Gene Roddenberry had no idea what Drake's equation actually looked like. So under the pressure from the studio to submit his proposal on time, he simply scribbled something random on a piece of paper and sent it in. Now, luckily, the studio also had no idea what Drake's equation actually looked like, and Star Trek was approved. Legend has it that many years later, Professor Drake was actually invited aboard Star Trek to scientifically advise an episode of Star Trek Voyager. And when he was on the set, he was shown this fake Drake equation that Gene Roddenberry had penned in his name. And when he saw it, he simply laughed. He said, "Oh, Gene, why would you write that? Don't you know that raising something to the first power is simply itself? Like, why would you do that?" So here's what the Drake equation actually says. Again, it's trying to estimate the number of transmitting civilizations in the galaxy. And unfortunately, tonight, we don't have time to go through every single one of these factors, but suffice it to say that those shown in red, these last four factors, are really hard to know. They deal with things like the emergence of life and the lifetime of transmitting civilizations. These are things that we still have no idea what they are today. But the first three terms, those shown here in blue, are astrophysical quantities. These are numbers that we can actually try to observe in the universe today. So if you took just those first three numbers and you multiplied them together, you would get the number of Earth-like planets in the galaxy. That would be the number of stars in the galaxy, multiplied by the fraction of those stars that have planets, multiplied by the number of Earth-like planets per planetary system. Now, Gene Roddenberry also still had no idea what this number was back in the 1960s. There was just no way for him to know. But no matter what this number was, he knew that it was going to be huge, right? Because the number of stars in our galaxy is literally astronomical. So when you discover what this number is tonight, you have a choice to make. You have a choice about how you're going to feel about this number. Are you going to feel small because you're just one being on a tiny mote of dust floating in a vast cosmic void? Or are you going to feel large because you are connected to this grand evolving universe of ours, and special because despite all those possibilities, despite what might be out there, there is still only one, just one of you. This is the kind of mathematical philosophizing that Dr. Leonard McCoy brought to his captain, Captain James T. Kirk, in an episode of classic Star Trek called The Balance of Terror. In this episode, Captain Kirk is pitted against an equally formidable Romulan captain, and he's feeling the draining weight of Starship Command. He's second-guessing his every move. He just wants a vacation. So Dr. McCoy comes to his captain to spur him back into action, and he does so by prescribing a very peculiar, though very potent medicine: the mathematical probabilities of the universe. This is what Dr. McCoy says to Captain Kirk. In this galaxy, there's a mathematical probability of 3 million Earth-type planets. And in all the universe, 3 million galaxies like this. And in all that, and perhaps more, only one of each of us. Don't destroy the one named Kirk. It's a very powerful scene, a scene in which Dr. McCoy makes a claim that there are 3 million Earth-type planets in the galaxy. Well, let's see how right he was. Today, we know that there are some 200 billion stars in the Milky Way galaxy. Now, this isn't an exact figure. This is just an order of magnitude estimate, but it'll suffice for our purposes tonight. Thanks to the Kepler Space Telescope, humankind's greatest planet-finding machine to date, and the TESS telescope, which will soon surpass Kepler's exoplanet-finding prowess, we now know that the fraction of stars that have planets is essentially 1. That is to say that basically you look up at the night sky and every single star you see on average has a planet going around it. And thanks to the hard work of astrophysicists around the globe, we now know that roughly 1 in 5 of those stars has an Earth-sized planet orbiting in its star's Goldilocks zone. So if you multiply these 3 numbers together, you get something like 40 billion. 40 billion. And remember, a billion is 1,000 times more than a million. So Dr. McCoy was off in his estimate by a factor of over 10,000. Yikes! Well, it's okay. We'll forgive Bones. After all, he'd love to remind us, damn it, Jim, I'm a doctor, not an astrophysicist. Okay, so one criticism that you could make of the Drake equation is its requirement for Earth-like planets. And it's quite possible that we need to cast a wider net in order to truly appreciate the diversity of life in the universe. You know, what if some life out there is nothing like us? And great thing is, Star Trek has explored situations like this. In the classic episode called The Devil in the Dark, Kirk and his crew encounter the Horta, a monster that was terrorizing a group of colonists, but in reality turned out to be a mother trying to protect her young. This creature eluded Starfleet sensors because, as Mr. Spock explains, life as we know it is universally based on some combination of carbon compounds. But what if life exists based on another element? For instance, silicon. To which Dr. McCoy replies, "You're creating fantasies, Mr. Spock." But it turns out that Spock was right, as he often is. The Horta is a silicon-based life form. But I think that Dr. McCoy was absolutely justified in his skepticism of Mr. Spock's suggestion. Let's take a deeper look at why. So silicon is often considered to be a good alternative to carbon because it has similar chemical properties. For instance, it has 4 valence electrons, which means that it's able to bond to 4 other atoms, just like carbon. So here's methane, CH4, 1 carbon and 4 hydrogens, and silane right next to it, 1 silicon and 4 hydrogens. They look practically the same. But if we scratch just a little bit deeper at the chemistry here, we start to run into some pretty profound problems. You see, chemical bonds are rarely equal sharing. And this carbon-hydrogen bond, the carbon atom actually tugs on those electrons a little harder, which means that the electrons in this molecule of methane tend to spend most of their time clustered around that central carbon. However, the polarity of this bond is reversed when it comes to silicon and hydrogen. The hydrogen is actually more electronegative and tugs on those electrons harder, meaning that in silane, the electrons spend most of their time on the outskirts of this molecule and make it extraordinarily reactive. In fact, it's so reactive that silane spontaneously combusts, which is probably why you've never heard of it before. It doesn't really exist in nature. So, you know, going to engineering now, which is not my expertise, but I do know enough about engineering in Star Trek to know what is the first thing that all the engineers in Star Trek try to do when they're trying to solve an issue. And that is to reverse the polarity, right? Well, here's an example of how reversing the polarity is absolutely critical. It's literally the difference between a stable molecule of methane and a molecule that spontaneously combusts in silane. Now, life on Earth also needs to constantly replenish itself with new materials. And on Earth, life gains most of its carbon from CO2, which is a largely unreactive gas. It floats around the atmosphere and then is accessible to life everywhere. Now here's SiO2 on the surface. Again, it looks very similar to CO2, but if we dig deeper, we run into trouble. It turns out that SiO2 likes to bond with itself to form complex matrices. In fact, SiO2 has a more colloquial name that you may know: quartz. So unlike CO2, which is a gas and wafts around everywhere, a silicon-based life form would need to stand basically right next to a piece of quartz to get its silicon. Not very accessible to life as we know it. So let me be clear. I'm not trying to say that that Star Trek was wrong in some way by depicting a silicon-based life form in the Horta. I'm saying that Star Trek was right by continuing the dialogue between Spock and McCoy in this way, where Dr. McCoy says silicon-based life is physiologically impossible, especially in an oxygen atmosphere. He's absolutely right. To which Spock replies, "It may be, Doctor, that the creature can exist for brief periods in such an atmosphere before returning to its own environment." And that's exactly what we see in The Devil in the Dark. But the main lesson from the Horta is that our chemistry may not be universal or fundamental to life. The Horta, in fact, is an amazing science fiction example of how we need to be open-minded when it comes to life elsewhere. The things that we assume to be fundamental to life, just because they are universal to life on Earth, may actually just be accidents of the way that life emerged and evolved here on our planet. And if this is the case, how might we truly go about detecting alien life? To find truly alien life, I think we need to develop a framework of agnostic biosignatures. So let me break this down for you. What does this mean? Well, a biosignature is just a feature that indicates or suggests the presence of life. And we tag on this term agnostic to say that this biosignature is not specific to life as we know it on Earth, and that it's capable of detecting unfamiliar forms of life as well. To introduce my philosophy on agnostic biosignatures, let me turn to another first contact in Star Trek with a wildly different kind of life form. This is the Calamarain from the Star Trek The Next Generation episode Deja Q. These creatures are plasma-based. They are completely different from anything remotely resembling life as we know it. Let me share the dialogue from the scene where the Enterprise scans the Calamarain and determines that it is a life form. Worf says energy patterns are reading as highly organized, and the computer reports signal patterns indicate intelligence. So the highlights here are driving out what I think is important: patterns, organized patterns, intelligence. This is what I think is important to understand about agnostic biosignatures, that life is a complex system, and complexity is maximized somewhere between complete orderliness and complete and utter chaos. In other words, life is the way in which information structures flows of matter and energy, and that structuring leads to complexity that I think can form the foundation for approaches to searching for extraterrestrial life. And so what I'm going to do for you now is give you a whirlwind tour of 3 examples of agnostic biosignatures that have been developed in just the past couple of years by the astrobiology community. Now, I'll warn you, a lot of these strategies are going to use some big words that sound like technobabble from a Star Trek episode, but they are real scientific terms, and I'm super excited to share them with you. So the first technique is something called chemometric fingerprinting. This was developed by Georgetown University professor Sarah Stewart Johnson. The idea here is to use DNA strands as sort of like different color sticky notes. And the more complex your sample is, the more different kinds of DNA sequences you'd expect it to bind to. So a simple sample, like an ordered crystal, non-living, will only attract a few different kinds of DNA, but a complex sample, like an alien life form, will interact with all kinds of DNA. So basically here, we're measuring complexity by the diversity of DNA sequences that your sample from an extraterrestrial world interacts with. Another strategy is called the molecular assembly theory or molecular assembly index. This is pioneered by Glasgow University professor Lee Cronin. And it basically asks, how many unique transformations must I make to construct an object of interest, whether it is a series of building blocks or letters that create a word or chemical bonds that create a molecule. Here, we're basically measuring complexity as the number of unique steps that it takes to construct a molecule of interest. And I like to think of this as the Lego principle. You know, if you go out to the store and you buy a Lego set, if that instruction booklet that comes with the set is super, super thin, you know it's an easy and very simple set. If that instruction booklet looks more like a dictionary, then you know you're going to be spending a lot of time and energy and information processing to construct the final product. And the cool thing is, it seems like molecular assembly is able to differentiate things that only life can make from things that can be made without life. So I'm showing you 4 different molecules here: ATP, penicillin, tryptophan, and asparagine. All 4 of these molecules are used in life as we know it. But life is the only process that is known to be able to make ATP and penicillin, whereas tryptophan and asparagine can be made abiotically. So there seems to be some cutoff around molecular assembly number 15, where above that, only life is known to be able to make those molecules. And beneath that, life or abiotic processes can create that. And finally, I want to tell you about a technique that is pioneered by my friend and colleague, Dr. Stuart Bartlett, right there in Pasadena, California at Caltech. Stuart and his team have devised a way to measure the complexity of a whole planet. Given a series of observations of an extraterrestrial world over time, you can basically then ask, what is the minimal model required to reproduce and predict that data that you gathered? And so in this method, complexity is measured by the size of the model needed to reconstruct the data set that you took. And so what Stuart and his team did was that they took data from the Earth and data from Jupiter and degraded that data to be what it would look like if those were exoplanets orbiting a very distant star. And then they calculated the statistical complexity. And here I've shown you a plot of the statistical complexity of Earth, shown in cyan, and Jupiter, shown in the magenta. And what they found is that Earth's complexity is a good 50% greater than that of Jupiter's, and that this complexity may be related to the activity of a thriving biosphere right here at home. Okay, so I'm getting towards the end of my talk. This last portion of my talk, I want to warn you that there may be spoilers. Well, there will definitely be spoilers for season 2 of Star Trek Picard. And I completely understand if you haven't seen this season yet, because it only finished airing a few weeks ago on Paramount Plus. And if you prefer to be unspoiled, then I suggest that you mute me and come back in about 5 minutes. But I really hope that none of you go away, because this plot is going to take us to some really, really cool scientific areas. So you've been warned, and here we go. So season 2 of Star Trek Picard takes place not too far away from where Cameron is right now. It takes place in Los Angeles, California, in the year 2024, just a few years from now. And basically, the premise of this season is that our heroes from the future come back in time to ensure that the launch of a crewed mission to Europa proceeds as planned. Rene Picard, pictured here, who is Captain Jean-Luc Picard's ancestor, is one of the astronauts on that mission. And her destiny is to find evidence of the first alien life form known to humanity. Okay, so let's say you're Rene Picard, about to blast off to Europa in search of life. What are you going to look for? Well, just as a reminder about your destination, Europa is a moon of Jupiter and is a prime astrobiological target. In fact, NASA JPL is currently building a mission called the Europa Clipper to visit this enigmatic world and search for signs of habitability and life. Now, Europa is a so-called ocean world because beneath its thick ice shell is a vast global ocean of liquid water. But what besides water makes this ocean habitable for life? What makes it a great place to make a living? After all, water is not the only thing that life needs. In fact, in a pure water solution, life would quickly starve and suffocate. So fundamentally, life requires energy, and we get our energy from the food that we eat and the air that we breathe. And we think that on Europa, there's just the right amount of flux of food in terms of stuff that comes out of hydrothermal vents, and also a flux of quote unquote air or oxidants that are created through the radiation that pummels its ice surface. And that this would be enough to sustain a biosphere underneath of that ice. And so basically, the lesson from Europa is that life is flux. You've got to eat, you've got to breathe, and yes, you need to excrete too. In fact, the gases that life exhales can be a very, very powerful biosignature. So, sounds like Europa is going to be a great place for René Picard to find life. The only thing is, we were thrown for a little bit of a loop in season 2 of Star Trek Picard, because according to Jean-Luc Picard's history books, René Picard is not destined to find life on Europa, but on Europa's sister moon, Io. And my jaw dropped when I heard this dialogue, because although Io is an ocean world just like Europa, its ocean is of a very different flavor. Its ocean is magma. It is liquid molten rock. So any life that you would find on Io must, by definition, be fundamentally different in nature to life on Earth. So that makes the task even harder. If you were René Picard, peering out your window at Io, taking readings, looking for truly exotic life, what would you look for? Now, I know this question seems daunting, but if you've been listening to this talk for the past 20 minutes, you know the answer. Number one, you would look for chemical components, and you wouldn't discount anything, because life on Io would certainly not have the same biochemistry as life on Earth. This was our lesson from the Horta. Number two, you would look for active fluxes of materials and gases that correspond to what life would do in this particular environment. This was our lesson from Europa. And finally, you would search for complexity, structures and patterns that could only have been created by an evolutionary process. This is our lesson from the Cala moraine. These are the three things that I think you would want to look for to identify life as you do not know it. In fact, if I had to venture a guess, these are the three things that a tricorder scans for when you are looking for life on the surface of a planet or scanning for those precious little life forms from orbit. Look, as Cameron said, I am not affiliated with Paramount or Star Trek. I am not one of the official science consultants. I don't know why a tricorder is called a tricorder, but if I had to make something up, in my headcanon, this is what it would be. These are the three elements of agnostic biosignatures. These are the ways that we would seek out new life. And the amazing thing is, scientists are working on these right now. You don't have to wait till the 24th century to be the next Catherine Janeway or Data. You can join us today as we explore space, the final frontier. Your captain's chair is waiting. The future is yours, and I'll see you out there. Thank you for listening. I'd be happy to take any questions that you have. Before I do, I just want to plug my podcast, Strange New Worlds. There's so much science in Star Trek that I couldn't fit into this talk, but if you want to learn more, go check that out. You can also follow me on Twitter. I'm at MikeY, M-I-Q-U-A-I. And I want to give a special shout out to the two actual Star Trek science consultants, Dr. Aaron McDonald and Dr. Mohammed Noor. Without their contributions, none of this would exist. So I think I'll jump off share screen now and we can have a nice conversation. Thanks for listening, everyone.
That was great, Mike. Thank you. Yeah, excellent. I've listened to your podcast a couple of times and I'm eager to do so again. So keep up the good work with that.
Yeah, thanks.
Okay, so as Mike said, if you have questions for him about the topic of his presentation, feel free to ask them in the comments section of YouTube or Facebook or wherever you're watching this, and I'll transfer them over and ask Mike right here. We have a few already. Let's see. Oh, people are asking you to put your Twitter handle in the in the YouTube
Oh yeah,
chat
yeah,
so they know
sure.
how to track you down.
Yeah, let me do that. Let's see here. Where is the YouTube? There it is. Okay. There it is.
So yeah, feel free to ask questions, everyone. Oh, interesting. Let's see. So yeah, I guess, well, I'm just curious. So you've watched some of the Star Wars canon films and such, maybe not as much of the expanded universe and such, but what do you see as the primary kind of contrasting the two universes? What do you see as some of the major differences between the two? I mean, I have my own opinions, but I'm curious to get your on this as well.
Yeah. So I guess I should say what I've watched. I've watched all the feature films. So all well, there's the 9 episodes, and then there's Solo and
Rogue One.
Rogue One. So I guess 11
so 11
yes.
films, and then now all of these television shows that have been
right. Yeah, I've watched Mandalorian and Boba Fett. I've watched some of the Clone Wars, but haven't made it all the way through that. But yeah, so there's a lot of the TV shows that I haven't watched yet. But yeah, my general impression of Star Wars is that it is really more like science fantasy and doesn't really strive to explain the scientific basis behind some of the things in the shows and movies, which is totally fine. I think that's super. It's
no, I
totally
agree
fine.
with you totally on that front. I think the story is foremost in kind of Lucas's writing and some of the co-authors' writing, and then the science is kind of secondary, more space opera-y as opposed to traditional science fiction-y.
Right.
Yeah, I think it's enjoyable, but yeah, I think it has its limitations in that perspective.
I think it's in the premise too, right? It's a long time ago in a galaxy far, far away, whereas Star Trek is, our future. It's meant to be our future or something very similar to our future. And so you can sort of see the ties to current day technology. Sometimes they reference things that have like happened here in our time. And so I think the purpose is a little bit different in that Star Trek is trying to show where we can get, and Star Wars is showing this like amazingly epic universe with like lightsabers and giant space battles. I feel like the genres are just different and they serve different purposes, but you can love them both.
Indeed. Let's see. Here's a question on YouTube from Huang Long Li. Do you think that an advanced civilization can exist on an ocean world? You were talking about Europa, you were talking about Enceladus and so on and so forth. If yes, I mean, so this person is basically saying it's impossible to have fire. I mean, one can have fire, but obviously it's more problematic in some sort of water world to find fuel for fire, and it's more easily quenched, especially on some of the ice worlds that we know about where it's particularly cold. So can you think of other ways in which they could potentially advance? Because generally, yeah, I guess we see advanced civilizations, advanced societies as coming up with technological breakthroughs that usually, at least here, started with fire to protect us from wild creatures and so on and so forth. But maybe that's not necessary in a different environment. I mean, I guess we're really biased by our own experience here versus what might be the possibilities abroad.
Well, I think that's a great point to start off with. Everything in astrobiology is inherently biased by what we have here on Earth, right? Because we are the only life that we know of in the universe. So getting to this wonderful question, it really depends on what you define as a civilization. Do you need fire to be a civilization? Do you need to smelt metal? Do you need that kind of technology that we have? Or is civilization more defined by the structure of the relationships between organisms? The fact that you have a close network of organisms that maybe have certain kinds of settlements. Maybe civilization is more so defined by the culture of a species rather than its technology. The technology that would be created on an ocean world is completely different, but we do see tool-using organisms here on Earth. In fact, in the ocean, like octopi, right? There are some astrobiologists at my old university, the University of Washington, who literally study octopus intelligence as an alternative form of intelligence that has evolved here on Earth through a very different lineage from us. And yet, this could be a model for completely different intelligences that we might find on ocean worlds or just any other world in general. The fact that intelligence has arisen multiple times here on Earth just makes the possibilities even greater for looking elsewhere. And so I wouldn't discount civilizations on ocean worlds, but they wouldn't look like civilizations here on the surface of our planet.
Indeed. You talked a little bit about biosignatures and technological signatures. How far are we from actually being able to see these sorts of things with the current technology and current instruments that we have access to?
Yeah, that's a really good question. So you all may have heard of the JWST launch. I believe that was like Christmas Day of last year, right? Really exciting. And the reason why so many astronomers were looking forward to that launch is because JWST will give us finally, hopefully, fingers crossed, the ability to peer into the atmospheres of worlds roughly the size of the Earth and get to know their chemical compositions. And so we may be able to detect our first signs of biosignatures on roughly Earth-sized planets using this magnificent instrument that appears to be working perfectly. And so I'm really looking forward to this. The things that people are going to be looking for are mainly CO2 gas and methane gas. These are molecules that are very important for habitability on our planet. CO2 obviously is a greenhouse gas. We're all very worried about increasing the CO2 too much and inducing, climate-related disasters, which is a very legitimate concern. But without any CO2 in our atmosphere, Earth would be actually too cold for life at all. So we do want to be able to find some CO2 around these exoplanets. And of course, methane is a gas that is produced by life. So hopefully we'll be able to find those things. And I'll be back at another Astro and Tap to tell you what they mean.
So we can see that in transiting exoplanets, just the light transiting through the atmosphere, and we look for that in the spectra or something like that? That's
exactly right. Yeah. So as a planet passes in front of its star relative to our line of sight, that starlight will filter through the planet's atmosphere, and we can look at the absorption lines in those atmospheres to find the fingerprints of these gases, essentially. And that's the hope, that we'll be able to do this with JWST.
And with technosignatures, there's been a lot of talk of this, and usually when I think of technosignatures, the search for technologically advanced civilizations, and I guess this ties in with the Prime Directive and all of these sorts of things. But the film Contact that came out, the book and film that came out 30 years ago or so, 20 years ago is when the film came out, by Carl Sagan. That's dealing with the idea of SETI listening in the radio part of the spectrum for any kind of non-artificial signals that couldn't be well explained from other sources. But now it occurs to me that SETI is also not just looking in the radio part of the spectrum, but also in like the optical part of the spectrum for any kind of flashes or whatnot. Which do you think is a better, I guess perhaps we should spend money trying to discover all of these things, whether it's just biosignatures that isn't the sign of a technosignature, but which do you think is probably more promising to look at for technologically advanced civilizations, or just any kind of life forms at all?
Wow, what a great question. I'm going to be politically correct here and say both. We need to do both, like you suggested. Why not both? And so, I mean, here's the conventional wisdom is that, there should be more biosignatures out there than technosignatures because you need biology to evolve first before our technological civilization. But then on the other hand, you need to weigh the fact that technological civilizations, technosignatures may be more easily observable, even if there are fewer of them, or they may last for a very, very long time if that technological civilization has achieved some kind of, homeostasis that allows them to persist for an extremely long period of time, or their technology just persists longer than the civilization does, and that these civilizations can then spread across the galaxy and maybe populate other planets. So those are the sorts of things that you need to weigh in your head when you think about, was it more likely to find biosignatures or more likely to find technosignatures? And I honestly don't know the answer. I think that the jury is still out. And back to your point about getting, more wavelength coverage, going into the optical instead of the traditional radio wavelengths. This is really important to do because I believe there was a study done by Jason Wright, who does SETI stuff, where they basically made the analogy to like searching the ocean for fish or whatever. And if you think about the volume of space that we have searched for SETI, in addition to this narrow wavelength range that we've been doing SETI over the past 50 years or so, that is equivalent to like,
it's just like looking for green fish.
Yeah,
20 feet of us or something like that.
Right. They did this analogy. The calculation was basically, it's like searching. We have searched a swimming pool sized volume in the entire ocean, right? Which is basically nothing.
Right.
And so I think a lot of, we should encourage SETI. We should encourage biosignature research. We're just at the beginning of this journey.
That's exciting. Sorry, I've been hogging the questions instead of allowing our audience members to ask their own. Sorry, audience members. Eat Nada One asks, in your opinion, is it more exciting as a scientist to find biosignatures from an exoplanet or detect a simple life form on a moon in our solar system? And I guess, which do you think is more likely? I mean, we obviously have much more detailed observations and even sample return from the structures, the planets, and the locations within our solar system because it's just, in our neighborhood, as opposed to getting photons from distant worlds. But obviously the distant worlds, that's a much larger volume that we're able to probe than just our little tiny neighborhood. Do you think one is more likely than the other to yield a discovery first?
Oh, wow. Another exciting question.
Sorry, these are just all speculation questions.
All speculation right now. And people have asked, there have been whole debates and panels about this where, somebody is Team Europa and somebody is Team Exoplanets or Team Mars or whatever. And they all go at it and say, I think, so obviously, as you said, Cameron, the case for the solar system is that it is easier. We have way more ability to actually get up close and personal with these planets and take samples and use more techniques to verify that we're actually looking at life. We can literally take a microscope and see something wriggling. You can't do that for an exoplanet. On the other hand, exoplanets have the power of numbers. There are thousands of them that we've discovered, and we're just discovering them by the bucketful each day. So we can, maybe just rely on that and sort of get a statistical sense, a survey basically of all of these potentially habitable worlds. And if a lot of them seem to have like oxygen in the atmosphere, maybe that's telling us something about the prevalence of life. And so again, this is something where I don't know the answer to, but it's so exciting that we could potentially know the answer to this in the next couple of years to decades. So that's mind-blowing, and we're really just entering this golden age of astrobiology, I think, where we will be finding out the answer to whether or not we're alone, hopefully.
That's true. There are lots of good questions. A bunch on warp drive and the Alcubierre drive and hyperspace and all of this and superluminal travel. I don't know. Do we want to delve into this right now? This seems like this might be a deep dive.
Yeah, I'm going to pass. I've said what I wanted to say about warp drive.
Okay.
I mean, I remember 5 years ago at our event, Cameron, some Caltech, I guess they were maybe an undergrad or grad student, raised their hand and said, like, if you could travel faster than the speed of light, doesn't that break causality? And I was just like, I guess, I don't know. I'm not an astrophysicist. I'm a planetary scientist. Like, yeah.
Yeah, it seems problematic. Anytime you travel faster than the speed of light, which of course is forbidden formally by general relativity and special, I guess both, but mostly by special relativity. First of all, it's impossible to get enough energy to achieve that kind of speed. It would take basically all the energy in the universe in order to achieve that speed. But even with some of these cheats, like the Alcubierre drive or warp, or basically like wormholes, people are familiar with this idea of wormholes, which was formalized as the Einstein-Rosen bridge, which has theoretical underpinnings. But it seems problematic in that, yes, causality gets broken once you get to a distant location faster than light or information could travel there. You could basically you can have events occurring before they should have in some capacity, in terms of receiving information about something that you wouldn't have known about, that would cause you to halt the first thing that caused the original action, these sorts of things, which end up with lots of paradoxes. So it seems really problematic, and I haven't yet seen a very, I'm not a numerical relativist, I'm not a general relativist, but I haven't seen any convincing arguments for how to not break space-time when you do those sorts of things. So yeah, it's sad. I was thinking about this a lot recently, because almost all science fiction has some ability for either faster than light travel or faster than light communication. I mean, Star Trek is rife with it, Star Wars is rife with it. And the fact of the matter is, the universe is pretty spread out. And the way currently, the speed of light has a finite travel time. And based on the distances away that things are in the universe, and the light travel time being, or the light travel speed being what it is, it basically implies like you have to wait a super, super long time relative to a human lifetime to get transport between these locations. Alpha Centauri is a few light years away, which with conventional rockets, even accelerating the entire time, means, thousands of years of travel time to get to these places. And that's a bummer. That doesn't make for exciting science fiction. It certainly doesn't, because everything's just super, super slow. But it may be that there are advanced technologies and paradigm shifts that need to occur within our understanding of physics. But at least according to the laws of physics as we have them now, it's not merely a technology thing. It's not like, oh, we need the next version of computers or lasers or something like this in order to make this happen. These are physical limitations of how quickly things can move. And, honestly, the speed of light's really slow relative to the distances. If we travel at the speed of light, which of course we can't, into the outer solar system, it takes us a long, long time to get anywhere, which is a bummer, because you think it's just like, boom, I'm used to moving fast. I'm used to having, instantaneous transfer. And it's just, the speed of light is slow. There's actually an Astronomy on Tap talk from like a few years ago that's in our archives if people want to look through them. I think it's called The Speed of Light is Slow. And it's pretty well demonstrated in his talk.
So one thing that science fiction often proposes to sort of deal with this problem is the idea of sleeper ships, where you kind of like, sure, you go to bed and I don't know, cryo, like you're in suspended animation or something,
1,000 years or whatever.
Yeah. What do you think about that? Do you think that's something plausible for us to try to do?
I mean, we do have demonstrations of animals that, like bears, go hibernate for the winter, and sure, they continue to burn a lot of calories in that time, but they are able to basically get in this sort of lower level bodily function stasis, where they can hang out and not burn as much as they would actively. And there are other organisms like water bears. What's the
tardigrades?
Yeah, tardigrades, that can basically go into this kind of stasis for as far as we know, indefinitely and come back and be totally fine once they basically come back. So I don't know. I think that's a promising direction. And honestly, a lot of these technologies just need a lot of funding that goes into them. Unfortunately, the ones for cryogenic like stasis are reasonably well funded because rich people want to live forever. So they want to freeze their head when they're just before dying so that they can come back 1,000 years from now when we can reanimate them. So if people want to dump money into this, it will be not just good for rich people to live forever, but also the rest of us to maybe travel to a distant star system. But yeah, I'm not a medical doctor. I'm not a physiologist, so I can't really speak to the veracity of these claims, but it seems promising. It seems interesting. Okay, so let's move on. We'll come back and we'll have more chats in a moment. But I'm gonna try and give my talk about the science of Star Wars. Here, let's see if I can. I've never introduced myself before, so I'm Dr. Cameron Hummels. I'm your next speaker, and I'm a computational astrophysicist here at Caltech. I normally study galaxies, how galaxies form, how they evolve, using computer models, basically building enormous models inside of our computers so that we can artificially speed up time to follow their evolution over millions or billions of years. And I'm a big fan of Star Wars. I've been watching it since I was a little kid. I can't claim to have watched I've watched all the films, obviously. I haven't watched every episode of The Mandalorian yet, sadly. I haven't had enough time, but I know a decent amount, but I'm sure there are people in the audience who are super fans who know more than I do about the Star Wars universe. But today I'm going to talk about the science of Star Wars. So let me share my screen here. Oh, that's the wrong ones. Okay, here we go. Hopefully people can see this okay. The science of Star Wars, and it's me. Okay, so the main question I get from a lot of people is there any real science in Star Wars? As we were just discussing, Star Wars is more like a space opera that's kind of set in a scientific environment or a futuristic environment more. And relies less on the science itself in describing the way in which events unfold, unlike some other more hardcore science fiction like Star Trek or some of the other universes written about or filmed about. And so basically in preparation for this talk, I sat down and I watched the original trilogy, and I came up with a ton of different questions related to how do scientific things actually take place within the Star Wars universe. And this is just from the original trilogy. There's a lot more science that gets touched on in some of the updated, both in the prequels and the most recent trilogy that came out. Not to mention Rogue One and Solo, and now these television programs which touch on all sorts of aspects of things. And so I started preparing my presentation, and I kind of focused. I went down a rabbit hole about lightsabers because I think lightsabers are pretty interesting and pretty fun. And ultimately, that's all I ended up responding to. I'll try and address some of these other questions from if you guys have questions, I can try and address them. But the main thing that I kind of engaged in is lightsabers. So hopefully that's okay with you guys. So for those of you who aren't familiar with lightsabers, here's Rey holding one. It's like a sword. The lore associated with it in the Star Wars mythos is that, only the Jedi or the Sith or other force sensitive people were able to produce and control these things, use them in some sort of manner as a weapon that was considered more refined than using a gun, which in the Star Wars universe is usually referred to as a blaster. They're powered by this kind of mysterious Kyber crystal that's found on certain places. The Kyber crystals were seen to tie into the Force, this kind of universal force that pervades the entire universe. And again, is another topic that we could discuss, but it's a force that pervades the entire universe and seems to be tied to certain individuals and certain structures within it, but can be enhanced or manipulated to allow you to do all sorts of things, from telekinesis to telepathy to long distance transmission of information, these sorts of things. And then wielding the lightsaber was not just a matter of flinging it around, but you seem to have additional control if you were one of these force-sensitive people like a Jedi or a Sith or something like that. A couple of clips because Star Wars is awesome. So this will, again, to remind you what lightsabers are all about, we've got one of the iconic battles from The Empire Strikes Back between Luke and Darth Vader. Hopefully this isn't spoilers since it was 41 years ago. So you can obviously see they're different colors. Occasionally they clash when they strike each other. They don't pass through each other. Here's another clip from episode 1. Probably the best lightsaber fight that takes place in the entire series. We won't show the whole of it, but this is Obi-Wan Kenobi and Qui-Gon Jinn against Darth Maul. Again, you see different colors, different shapes for these things. And the choreography in that is so awesome. It's like the best part of that entire film. And then lastly, this just kind of showcases what they can do. In addition to just hacking away at people and burning through things, they can deflect laser beams. They can cut through walls. So you can see these are quite powerful. They appear to be these basically swords made of light or plasma or some other very hot substance that's able to cut through things. So here are some observations. It's sword-like with some sort of finite blade. It's not infinite. And there's a hilt that seemingly contains all of the power and the composition of it. It glows and it extends on the command of the user. There are different colored blades, you know, everything from the purple blade of Mace Windu to the green and red and blue blades, and now there's like a dark blade and all these different things in the expanded universe. But it cuts and it burns through different materials. It blocks other lightsabers, as we saw. They clash when they strike against each other. They can block blaster shots, essentially bullets from energy-based guns, and then they make these cool noises. So can we actually make a lightsaber? Do we have the technology, or even if we don't have the technology, is the physics there to actually be able to construct this sort of device? So first, let's talk about, would this thing be light-based, like a flashlight, like you kind of see here, or would it be something else like plasma-based? We can talk about that in a moment. So if it's light-based, let's think about the most obvious thing. Let's think if it's a laser. So let's talk a little bit about lasers and what they are and how they work. Probably everyone's familiar with lasers. They're pretty widespread. You can buy a laser pointer for $5 on Amazon. I actually have a laser pointer here that I use for events when I'm pointing to things in the night sky. And so I'll turn this on in my little screen in case you can see it. It's on right now, and you can tell it's on because I'm going to shine it right at my camera and hopefully not damage my webcam, but you can see that it's on. But when it's pointed upward, you can't see the beam. You can only see the beam when it's lit against my hand. And that's a key point here. Unless there's light, or unless there's some sort of particulate in the air, like it's foggy or dusty, you won't actually see the beam. You'll only see the beam if there's particulate in the air, something that the light hits and it scatters off of, and those photons eventually go to your eye and you can actually see the beam. But let's talk a little bit about what laser even means. People are probably familiar. It's an acronym. It means light amplification through stimulated emission of radiation. So let's talk a little bit about what that even means. So this is the Bohr model of the atom. You have your proton, your nucleus in the center, and you have an electron kind of in an orbit around that nucleus in some capacity. They each have a charge. The nucleus has a positive charge, and the electron around which the electron that's orbiting around it has a negative charge. And this is the simplest atom. This is a hydrogen atom, so it consists of one proton and one electron. But you have every element on the table of elements has a different kind of diagram with a different number of protons and an equal number of electrons that are present there. So in a hydrogen atom, when it has a low energy, we'll just say E1, that's usually when the electron in its orbital is closer to the nucleus. But for some reason, if that proton, or if that atom gains some sort of energy, perhaps by bumping into another atom at a high rate of speed, or absorbs some sort of quantum of energy from a photon, it can get bumped into a higher energy state, where essentially that electron is at a higher energy, and it'll just hang out in that energy state. But it won't hang out indefinitely in that higher energy state. At some point, it will spontaneously drop to that previous lower energy state. And in doing so, because energy is conserved in any closed system, the difference in energy between the high energy state E2 and the low energy state E1, it'll essentially take that difference in energy and it'll radiate it away in terms of a photon, a ray of light. And this is, as I said, this is spontaneous emission. This is one of the ways in which light gets generated from atoms in this way. So now imagine that you have a bunch of atoms all hanging out in that higher state, in this state, in the high energy state. So they're all hanging out next to each other, and all of a sudden we get one of those to spontaneously emit a photon. It turns out that, just based on the laws of physics, it turns out that the emission of that photon induces similar emission of photons from all the neighboring atoms. Not all of them, but there's a higher probability of emission. It's called stimulated emission because you're stimulating the emission from the emission of this original one. And the photons that get emitted tend to be the same wavelength. They tend to be the same direction, the same polarization. And so you end up with this beam of many, 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 many different photons all traveling together in the same direction and having very similar characteristics. And that is what a laser is. That's why when you look, well, don't look down a laser beam, but that's why when you point a laser beam, the beam remains very narrow and very collimated, and it's all the same wavelength, it's the same color. All of these things are due to this stimulated emission of radiation. So that's why lasers work. You can make them in different colors depending on what that energy difference is, because those energy jumps are very discrete. That's one of the consequences of quantum mechanics, is that you get these very discrete jumps in energy depending on the atom or the molecule that you're using. And so you can get red or blue or green or UV or very distinct wavelength, distinct color lasers. So, but in terms of how this matches with a real lightsaber, could we produce a laser that's a real lightsaber? This is a video that I found on YouTube from Simon Karbowski, and it just shows him pointing a bright green laser around in the fog. And you can see, like, it's a bright beam, right? We can see it. Of course, it's foggy. So like I said, there's lots of water moisture in the air that the laser beam is bouncing off of, and that's why it's reaching our eye instead of just being this invisible beam that remains collimated. But you can see that it's quite bright, and it kind of looks like a laser pointer. So it is sword-like. It doesn't have a finite blade because it's traveling indefinitely. You could imagine maybe having some sort of cap on the end of your lightsaber to prevent the beam from going off into infinity. You could imagine that. That might be a possibility. The blade glows. It doesn't necessarily extend unless you had that cap extend with some sort of mechanical device. You can get different colored blades, as we showed. You can make lasers powerful enough. The ones shown here are only a few milliwatts, so very, very low power. But you can buy a 5-watt laser online for a few $100, and it's very powerful and will do things like pop balloons and burn small things. There is some heat that gets distributed. I mean, lasers get used in all sorts of things, in surgery, like LASIK surgery, and you can get them powerful enough where they will cut through things. So yes, you can cut and burn through materials. Usually the power associated with that is pretty high, but it is possible. But because it's light, if you have two lasers knocking against each other, they're just going to pass right through each other. Like photons go right through other photons. There's no significant rigidity to it. Similarly, they're not going to block blaster shots. If somebody shoots at me with a blaster, my laser beam is not going to do anything to stop it. And it's not really going to make any cool noises unless I, rig it up with something. So it's not really a very good match for what a real lightsaber would be. Similarly, I just included this for completion's sake. You can buy these cheap telescoping light toys online. These are not lasers. These are essentially just like a flashlight and then some sort of plastic telescoping casing that you spend $20 on. And sure, it could be good for kids or whatever, but it's clearly not like it. Yeah, I guess it's sword-like with a finite blade and hilt, and it glows and has different colors, but it's not going to cut or burn through anything. And I guess it blocks other lightsabers because there's the rigidity of this case that runs into it, but it's not going to block blaster shots. And yeah, I guess it'll make cool noises because it has sound effects associated with it. But that's not really a lightsaber either. And if you spend on more expensive devices, usually these are fiberglass, like a fiberglass hilt with like an LED. So it's like a glorified fiber optic cable that has light traveling down that fiber optic cable. It's a higher end than those telescoping ones, but it's not going to do anything. It looks cool. It's cool for a Halloween costume, but it's not actually going to do any of the functionality that a true lightsaber is supposed to do based on the film and canon. Okay, so we've talked about light-based stuff. Let's talk about plasma-based stuff. So plasma, people may be familiar with the term plasma. This is not to be confused with the plasma in your blood, kind of the fluid state of your blood. Plasma is considered by many people the fourth state of matter. So if you think of different phases or states of matter, the three traditional ones that we oftentimes think about are solids, liquids, and gases. And essentially you can go from a solid to a liquid to a gas by increasing the temperature of it. And effectively what I mean when I say increasing the temperature of that substance is making the individual atoms or the individual molecules present in that moving around faster. That's what's happening on a microscopic level when we talk about temperature. If I stick my hand on a piece of ice and I slowly heat that ice up, the individual molecules of water that are present in that ice lattice, and you can kind of see that they look like a lattice here, slowly start to move around more because they're not really moving at all when they're frozen. And eventually they're moving quicker. And then we consider, once they break out of that lattice, that's when we consider it to be a liquid. And if they continue to move faster and faster, that we perceive that as it getting hotter and hotter, and eventually it becomes a gas. And if we continue that process and heat it up more, we can induce this state called a plasma. And essentially what happens is we take our good old view of the atom, the hydrogen atom, and somehow we either slam this into another atom so hard that it adds the energy to the electron and the electron becomes unbound. We can also do it through electric fields. We can induce this sort of effect, but there's a variety of ways in which we can inject energy into this. One is just, kinetics by slamming these things into each other faster and faster, or sticking a flame underneath, which is effectively doing that. And eventually the electron becomes unbound from the proton, and it's what we call ionized. It becomes ionized. And at that point, now instead of having a neutral thing where the proton was balanced by the electron, we have them separate, and we have separate charged particles. And when they're separate charged particles, then they behave according to, they feel magnetic fields, whereas they didn't really previously when they were just net neutral. And so that's why you see these pluses and minuses, is because it's like a plasma is like a really hot gas that obeys magnetic fields. So it behaves in really peculiar ways. Some examples of that. Oh yeah, this is just a bar magnet. This is not a plasma, but this is just to illustrate the magnetic fields and how the iron filings are aligning themselves according to the magnetic field lines associated with this bar magnet. And plasmas will as well. So there are lots of examples of plasmas that you may be familiar with. Neon signs are a form of a plasma. They're confined inside these glass tubes, but there's an electric field that's generated from one end of the tube to the other end, and so it effectively ionizes and energizes the gas that's in there, whether it's neon or sometimes it's other noble gases or hydrogen or helium or mercury. Fluorescent bulbs are the same effect. Welding torches, if they get hot enough, are producing plasma at their tips. Lightning is an example of plasma. When the glowing bolt of lightning is actually plasma flowing down this kind of crinkly, craggy little channel through the air, because you've broken down there's such a voltage difference between the cloud and the ground that it's ionized the gas in between it, and that's the channel at which the charge is dissipated across this broken down air gap between the two. The surface of the sun is a good example of a plasma as well. I mean, the entirety of the sun effectively is a plasma. The surface is just what we see, but the plasma goes all the way down at different temperatures. And you can see these arcs. These arcs are associated with the magnetic fields in the sun. And because this is all plasma, it abides by the presence of the magnetic fields. And so you see glowing arcs here because the plasma aligns itself with the magnetic fields that are present in the sun. And then on Earth, this is the interior of a tokamak, which is a nuclear fusion reactor for trying to kind of replicate the conditions in the interior of the sun here on Earth to try and generate clean energy. And this is a nice little GIF that's kind of demonstrating this effect. So the glowing stuff is the plasma, and this chamber in which it sits is the tokamak. It looks like a donut. We'll talk about it a little bit more in a second. So let's talk a little bit. So real world option number 4, okay, a blowtorch. If you have sufficient heat when generated in a blowtorch is essentially just the one or two different pressurized gases that are being ignited and oxidized, and they reach such high temperatures that the energy is such that it can break down the molecules or the atoms that are present in that fuel. So oftentimes you'll do this with acetylene or propane or oxygen. Usually it's a fuel and oxygen together and mixed in a particular way such that when you ignite it and when it's mixed in that way, it reaches these high temperatures, and the pressure that's coming out of the bottle allows it to expel outward and do whatever you're doing. So if you're trying to like weld something or cut through a particular metal, you want to have a very high temperature, and so this is what you do. So there are a couple. This was brought to my attention by some fellow postdocs and graduate students. I was totally unaware of this. There were a couple of attempts in the last couple of years to essentially make lightsabers using this sort of technique, and it's really just like a glorified blowtorch. Lightsaber. Okay, so the one on the left is the actual. Yeah, you can see it's like it's just like a big blowtorch here. The light's still on. And light's still on. The lightsaber. Okay, so this is from a YouTube site you can find. We're actually giving away this mace. Here's another clip where they're able to like cut through a metal door, which is pretty impressive. But you can see there's a guy who's wielding it has this enormous backpack. And that backpack contains the fuel, the propane and the oxygen fuel for the actual lightsaber. So he's got this steel door, pretty. Can you cut through that? Pretty heavy duty. And yeah, I mean, it cuts. It's pretty impressive, and it remains reasonably well collimated for the first, 12 or 20 inches of the beam before it kind of peters out. But it's pretty cool. It's pretty impressive. There's another guy here, Alex Lab, uses a different, there's some pretty cool music, I guess. It's a different mix of fuels to achieve the same sort of behavior. He doesn't have the pack on his back, so I imagine the fuel wouldn't last forever. But he's going to do the same thing, like cut through a metal block. So yeah, these things are getting to be, a few thousand degrees Kelvin, quite hot, and because they're so hot, they can melt through stuff. You can see it's not as trivial as you saw in the films, where they actually have to hold it on things for quite a while in order to melt through them, because those things have a decent amount of heat capacity, and they need to heat up before they can actually melt, right? So you can imagine a version of this that's more powerful because it's at a higher temperature, or perhaps it's at a denser amount, in the blade that more effectively cuts and more quickly cuts, but you run into logistical problems with that. But nominally, this is a possibility. And so you look at the things that it works like a sword. It glows. You can make it do different colors if you make it from different gases, or if you change it to be at different temperatures. And it'll cut and burn through materials, but it's not going to really interact with other lightsabers. Not really. And it's not really going to block any shots that are coming at you, presumably. And the cool noises that we heard, I think, were just added. I don't think those were actually part of the noise associated with the actual device. It's going to sound like a blowtorch. So then finally, the fifth option is kind of one that hasn't really been demonstrated. It was more just me thinking about and talking with a plasma physicist friend of mine, Matt Worstel, who's worked on this in the past. Well, he hasn't worked on lightsabers, but he's worked on tokamaks in the past and stellarators. And that's the idea of this nuclear fusion reactor. So magnetically confined plasma. We remember plasmas, because they have their constituents are charged particles. They behave according to the laws of magnetic fields. And so let's very quickly take a digression and talk about gravity and talk about the sun. So everyone, this will make sense in a moment, I promise. Everyone's familiar with gravity. Gravity is the force that holds us onto the surface of the Earth. Similarly, it works regardless of where we are on the Earth because it's an attractive force. And basically, it describes gravity as an attractive force where any two objects that have mass are pulled towards each other because of this thing we call gravity. And it's, we don't have to get into the nitty-gritty of how much and the intensity, but it's just basically an attractive force. So in the sun, all the individual parcels of gas that make up the sun are being pulled towards all the other parcels of gas that make up the sun. And so the net effect is this gravitational collapse. Everything's being pulled towards the center of mass. And so you get enormous pressures and enormous densities in the interior of the sun. Think about, you jump into the ocean or into a swimming pool and you swim to the bottom of the pool. The pressure in your ears gets really, really high because all those overlying layers of water are pressing down on you. It's the same thing if you don't want to jump into the sun, but as you go deeper in the sun, you have more and more of these layers that are weighing down on you. And so the pressure gets really, really high, and the density gets really high, and the temperature gets really high. And effectively what happens in the core of the sun is you get nuclear fusion. You get hydrogen atoms that get crammed so close together to other hydrogen atoms that they join together and they turn into helium atoms. And when they do that, they release an enormous amount of energy in the form of gamma rays, which are just energetic photons. Like, think of visible light and then bump it up by a factor of 1,000, or gamma rays, I guess it could be 1,000,000 even. And so that's why we see the sun shining, is because the energy that was generated in the core eventually percolates out to the surface and it shines, and those photons free stream outward. And that's why when we look up in the sky, the sun glows, is because this energy that was created through nuclear fusion eventually gets to the center. So this is basically free, clean, abundant energy. And I say free because you have to be able to cram protons and neutrons close enough to each other in order to achieve this. You have to essentially get the conditions in the interior of the sun in order to unlock this abundant energy that we call nuclear fusion. But we've been trying, we being scientists, I'm not a plasma physicist, but scientists have been trying to do this in the form of a few different ways for the last 50 or so years. So that we can essentially do nuclear fusion on the surface of the Earth and get this free energy where all we have to do is throw in hydrogen and then we get out energy, and it would be super great. And the byproduct is helium, which is great. It's not like radioactive baddies. So essentially the way it works is that you have magnetic confinement. You have magnetic fields. In this case, I represents current that's going through this white loop in the shape of a donut, and then that generates a strong magnetic field in the interior of that donut. The B here is the magnetic field, and the plasma flows along the magnetic field lines. And so essentially what you end up with is this donut-looking shape. It's called a toroid, but this donut-looking shape of coils, and inside you have this plasma that gets confined. You evacuate it, you create a vacuum inside that chamber so that the plasma is not going to run into other stuff, and then you you throw in your plasma, or you generate your plasma in there, and you try and confine it and get it to super, super high temperatures so that you can replicate the conditions in the core of the sun. And it looks something like this. This is the kind of the glowing, this is recombination light that occurs from that plasma in the interior of this tokamak chamber. Tokamak is a weird word. It's kind of an acronym in Russian, because I think the Russians were the first to come up with this technology. And it means something like, I forget the exact phrasing, but it means something like magnetically confined plasma, basically, in acronym in Russian. But everyone just calls this a tokamak. There are other designs for ways to constrain a plasma, but this is one of the most popular ones. And these images are taken from ITER, which is the International Thermonuclear Reaction Experiment, I think is what it stands for. But it's this international collaboration of different physicists to try and produce a nuclear fusion reaction that gets more energy out than you're putting into the energy. So you're getting a net out. And we haven't yet achieved that yet, but the hope is that at some point soon we will achieve that, and then we don't have to rely on oil and coal and all of these baddies. We have some sort of free, clean energy source. So anyway, getting back to lightsabers, since I really got off topic here, one can imagine that you can use magnetic fields in a variety of different configurations to contain and constrain the presence of that plasma. You could make a solenoidal magnetic field or a toroidal magnetic field to kind of contain that. But the problem is, so I guess you could imagine, like, you've got your lightsaber, right? And then you have some sort of method for constraining the magnetic field around this long saber shaft. And then the plasma lives inside of it. And of course, the magnetic field won't interact significantly with neutral objects like, this can of beer, although this is aluminum. So it would in some ways, but with this piece of paper, I could hold this up and hold up my magnetic field encasing plasma, and the plasma would cut through it, but the magnetic field wouldn't interact with it. So it's kind of like an invisible force field that keeps it in place. But the problem is we don't have a really good method for generating magnetic fields that are that strong, kind of away from the generation location. So having the magnetic field stick out here while our hilt is the thing that's generating. I mean, maybe that's something that we can do in the future, but that technology doesn't yet seem to exist. Right now, those tokamaks usually consist of these copper coils or superconducting coils that surround the whole thing to allow these super, super high currents so that you can keep these magnetic fields at like 15 Tesla, which is an enormous magnetic field strength. That's like about 1 million times larger than the magnetic field that we have from the Earth itself. I think that's right. Anyway, so the other problem is let's say you've got your solenoidal magnetic field that's containing this plasma along these different lightsabers. As soon as they clash, you might have a reconnection event that goes from the magnetic field of this one into the magnetic field of that one, and that would be bad. That would have like a huge amount of energy that would get released, and then they'd get wrapped up in each other, and the plasma from Darth Vader's red lightsaber would flow into Luke Skywalker's green lightsaber, and it could be a big mess. But more importantly, it would cause this big explosive event that wouldn't be good for either of them. I mean, it's good that Darth has like a helmet and stuff on, but it probably wouldn't matter much. They'd probably both get pretty beat up. So essentially when reconnection occurs, it allows these magnetic field lines to kind of join, and you have an explosive event and you have an outflow jet. So there's a nice little video that I found online from NASA. This is the Earth. This is the magnetic field structure of the Earth and the sun kind of hitting it. And you can see these magnetic field lines. When they start to get closer together, they'll get kind of pinched, which we're starting to see here. Let's see. So they're getting closer together, and eventually they'll like pinch and join. And that's the reconnection event. And when that happens, it basically releases a bunch of energy that rains down. I mean, that's part of what's responsible for the northern lights and the southern lights that we see here on Earth, are these sorts of reconnection events. So you wouldn't want that happening in your face when you're dueling Count Dooku or whoever your antagonist is in whatever particular film. And then the last thing I wanted to show is these things are hot. That plasma is really hot. it's on the order of a few thousand degrees. And similarly, so this is a personal video of mine. I was in Iceland last year at a volcano, and this is me getting lava from a volcano. And that was similarly hot. This is only like 2000 degrees Fahrenheit. And I was almost burning my face off. I'm wearing welding gloves and have this thing over my face to keep the heat off of me. And it was excruciatingly hot, and I could only stand there for like 30 seconds before I had to leave. And so I can only imagine what, Obi-Wan Kenobi with his lightsaber 3 feet from his face that's hotter than the lava is close to me would be feeling by igniting his plasma blade in front of him. The magnetic field's not going to do anything to stop the heat. So, okay, so in terms of real world option 5, maybe this is a real world option, magnetically confined plasma. You can do all these things. You can get it sword-like with a finite blade, and it can glow, and you can get different colors based on the temperature of your blade and so on and so forth. And it even makes cool noises and would potentially block blaster shots if those blaster shots were also made of plasma. However, it requires an enormous amount of power to generate this 15 Tesla magnetic field. It requires a constant supply of new plasma because plasma is going to slowly leak out where in between the field lines that are trying to confine it. And this is actually a problem that ITER and some of the other nuclear fusion projects have run into. And then there's concern with these magnetic reconnection events blowing up. And then there's concern with the intense heat near the blade. So could we really make a lightsaber? Maybe, I don't know. It's going to be hard, but the ones that were demonstrated on YouTube are pretty cool. They're just not like truly a lightsaber. I think this is more along the lines, but obviously has its own caveats and constraints. So I'm sorry I didn't get to other Star Wars, science of Star Wars. I got really down this rabbit hole, but it was fun. So hopefully you guys have some questions either about this or about other things related to the science of Star Wars, and we can handle that. So Mike, do you want to jump back in and we can field some questions? Okay, sweet.
Hey, that was awesome.
Oh, thanks, man. I
learned so much about, magnetically
confined
plasma.
It was great chatting with my plasma physicist friend. I was like, you got to tell me more about these. I know the basics, but I don't know if I can explain this to the real world. So let's see. Okay, so any questions from the audience? It looks like I'm going back through the transcript here to see what else is here. Aren't the lightsaber blades made of molten iron particles? I don't know. I've never seen that description. It's possible. What if the sun collapsed to a white dwarf earlier than predicted? I mean, we can talk about that. It'd be bad. It'd be bad. Yeah, it'd be bad. Yeah, I mean, our estimates for stellar evolution models that basically give us a prediction that the sun has about 4-ish billion years left in its lifetime are based on us running computational models, which seem to match observations reasonably well in terms of describing the behavior of different masses of stars and different types of stars and how they behave. But we've only been doing this for 50, 80 years trying to look at stars and model their interiors either through pencil and paper calculations or now through computational modeling. And stars take a really, really long time in some cases to change over their lifetimes. I mean, they're living for billions of years. So it's hard in some ways to extrapolate their full lifetimes and their full behavior. And it may be that the sun dies sooner or it takes longer to turn into a white dwarf, but it's unlikely that that's going to happen it's very unlikely that that's going to happen in a very short time scale. That's much more on time scales of billions of years. So don't worry about selling your real estate right now for fear of doom mongers here on Astronomy on Tap. Noel Rabina asks, can you really see stars like lines in Star Trek or Star Wars, like my background here? And that's a good question. I was thinking about that a bit. What do you think, Mike? I'm curious what your take on this is.
I have no idea. I don't know what it looks like to travel faster than the speed of light.
Well, yeah, it's problematic, right?
Yeah.
All of this is prefaced on something that doesn't actually happen. So, yeah, I mean, I guess if you were traveling faster than the speed of light in the sense of us thinking about, if I were traveling, think about something that's relatively stable on the horizon, and then I move really, really fast. Would those things start to blur because I'm moving so quickly that I would see them making up various different locations in my view? I guess it's effectively like a reverse shock wave. Like we're the thing traveling through. Maybe. I mean, it's a super cool special effect.
I know what you wouldn't see. If you looked backwards, you wouldn't see anything, right?
That's right.
Because nothing would be able to catch up.
Nothing would be keeping up.
Yeah.
Yeah, you'd be bumping into photons that had already passed through you. I mean, maybe if they were coming from the side, you'd see some stuff that was coming from the side because you wouldn't be traveling. Yeah, it's an interesting thought experiment. Let's see. When do you think we will, Ananda Ganguly asked, when do you think we will have useful nuclear fusion reactors? Ooh. I mean, the kind of joke is that everyone has been saying that we'll have nuclear fusion reactors in 10 years for 50 years. So it's this notoriously difficult problem to achieve. And there's been no dearth of people trying to work on this or money going into it because the like endpoint of all of this is an extreme amount of like wealth. Whoever invents this successful nuclear reactor is, if it's a private person, is going to be extremely, extremely wealthy because they can basically just produce free energy. The idea is that you put in X amount of energy and you get out X plus 5. And so you can do that repeatedly and then dole out all of your energy to, all the people who need it in the world. And everybody needs energy at some level. So there's been a huge amount of investment from these nations. I think ITER, the nations that are part of it are China, Russia, US, UK, France, Germany. I mean, it's major powers that have all worked together to try and do this. I think the location is actually in France, but it's exciting. But that's not the only way people have looked at doing nuclear fusion reactions. There's also inertial confinement. So rather than trying to confine your plasma with magnetic fields, you essentially slam a bunch of lasers together that are all hitting this pellet, this nuclear fusion pellet from all sides. And they hit it with so much inertia that it crams it together into this hypercritical dense location at super high temperatures and super high densities that you can achieve nuclear fusion in some sort of burst and then capture the output in some sort of reasonable way. And kind of, I feel like one of the main places in which this occurs is a place called NIF, the National Ignition Facility, which is in Berkeley. And they had some big announcement in the last year showing that they were able to achieve, I don't know, pretty decent amount of output, still not achieving more than they'd put in, but it was something like 50% or some factor of two-ish amount. You put in one energy and you get out 50% of that energy. So it's not break even, but it's getting close, a lot closer than it had been getting for a long time. So I don't know. I'm not a seer. I can't predict when that'll actually be the case, but it'll be a big deal and it'll be on the front page of every news, and it'll change the way we live our lives. And I'm hopeful that this will be in the next 10 years. But like I said, everybody's been saying this for decades. Let's see. Any other questions? I haven't looked at YouTube to see here what the questions are. Oh, yeah, sorry, I gave a spoiler about Star Wars. Hopefully I didn't mess it up for people. Yeah, it doesn't look like there's any major questions there. Anyway, if there are more questions, by all means, ask questions. Yeah, is there anything? I guess we'll just jump on to pub trivia. People probably want to hear pub trivia. You ready, Mike?
Ready. Let's do it.
Okay, sweet. Let me find this thing. So pub trivia is the way we've done it in the past. There is a website called menti.com that you can go to. There's no like login, there's no cookies, there's no fees or anything like that. You just go there and you enter in this code, and the questions will pop up not only on our screen here on the presentation, but also on your web screen or your whatever browser you use to go to this particular location. Let's see. Okay. How do I present? Okay. Can people see this? Can you see this, Mike?
Yep.
Okay, sweet. So this is it. If you go to menti.com and type in this code, then this will pop up and you'll get the questions as soon as I go to the next slide. And more importantly, when you enter in your answer, the answers pop up here so the entire audience can see what everyone wrote, and we can get a feel if people are getting things right or wrong or whatever. One thing to note is there are no formal prizes for this, so please don't cheat. There's really nothing to gain from cheating in this aspect. I realize that everyone has their computers and literally, all of mankind's knowledge of the universe at their fingertips. And so you could look up these answers and potentially get them right, or maybe not, I don't know. But I'd say give it a guess. And if you know it, that's great. If you don't know it, then give it a guess and do like you do in real pub trivia. If you don't know the answer, give it a funny guess. And everyone has a good chuckle. I have a good chuckle. So let's see. First off, this astronaut was the first Black woman in space and also the first astronaut to guest star on Star Trek. Who is she? This is a good question. I don't know the answer to this. I mean, I do now because you gave me the answer, but I didn't know the answer to this before you. I'm not that knowledgeable of Star Trek to have known this. Mae Jemison.
Ooh.
Okay. Oh, a couple of people guessing that one. Uhura. Oh, that's a good guess. She's awesome. Is Nichelle Nichols, she's still alive, right?
Mm-hmm. Yeah. She's been having some health issues, I think, but she's still with us. Yeah.
Cool.
She's retired from the convention circuit, though.
Has she? Okay.
Yeah.
How many of the original cast are still alive? Like,
let's see. There's Nichelle Nichols, George Takei, and
Leonard Nimoy passed, right?
Yeah. Who played Chekhov? What's his name? I shouldn't be forgetting names like this.
Oh, I'm not trying to put them. That's okay.
Yeah.
Is Chekhov still alive?
Yeah. Mm-hmm. And William Shatner, of course, is still alive and kicking.
Still kicking. Yeah.
Yeah.
Whoopi Goldberg. She is a character on TNG, isn't she?
Mm-hmm. Yep. Guinan.
Sweet. Okay, so the answer is indeed Mae Jemison.
Ooh.
I actually don't know a huge amount about Mae. What was the nature of her character and her cameo in the show?
Yeah, so she just played a simple, this Lieutenant Palmer in one episode of Star Trek: The Next Generation in season 6. She grew up a huge fan of Star Trek and especially Nichelle Nichols. So the person who put Uhura wasn't that far off, I guess, by association. The original character of Uhura inspired Dr. Jemison to become an astronaut, to go into space. And then LeVar Burton actually heard that Mae Jemison was a huge Star Trek fan and invited her onto the set to play the role of this character in an episode that he directed.
That's awesome. Oh, I didn't know LeVar Burton directed some of the episodes of TNG.
Yeah.
Cool. I like that guy. That guy's awesome.
Mm-hmm.
All right. What desert planet in Star Wars hosted 2 suns? I guess it wasn't so much that the planet hosted the suns, but the planet orbited 2 suns. Mm-hmm. But you can see 2 suns from the surface of the planet. Kind of a iconic one. Probably people know that.
Iconic, yeah. The music during those scenes during the sunset always reduces me to tears.
Yeah, pretty good. Sunny side up. I won't belabor this one too much, but it is kind of a talking point here. So everyone's probably familiar. Yeah, Tatooine is in fact the answer. known for its kind of iconic binary sunset consisting of two suns on the horizon. What's crazy, and I just learned this in talking with Jesse Christensen, who is an astronomer here at Caltech, who does a lot of exoplanet research and is the head of the NASA Exoplanet Archive that kind of characterizes and records all of the publications associated with different exoplanets, is that the first system that was discovered, there have been 16 separate exoplanetary systems where the planet is orbiting around a binary star, much like this situation. And the first one that was ever discovered was, this is an artist's illustration. It's called Kepler 16b. And there are indeed two stars, and the colors of those stars are yellow and red, just like what was characterized or portrayed in the original Star Wars film. These two stars. They did not have to both be, one is like a G star and one is like an M star. They did not have to be this color match. So Lucas has some sort of foresight in terms of being able to divine the nature of these sorts of things. But yeah, Tatooine, big fan. Tatooine is actually my license plate. Although the sad thing is, license plates, vanity plates, have to be 7 characters. And so obviously this is 8 characters. So I wasn't clever, and I didn't have like a number here, like a 2 for the 2. So I just did TATOOIN, and I was like, oh, that'll be good enough. No one will know. Everyone will know that this is Star Wars. And then I got it and I was like, oh, this is tattooing. So I've had a bunch of people come up and be like, so are you a tattoo artist? Could you like work on, I need some work on this one on my arm right here. And I'm like, no, I'm just a big Star Wars geek.
That's great. I love that
funny.
story.
It's pretty funny. So, okay. What famous physicist portrayed a holographic version of himself in Star Trek: The Next Generation, playing a poker game against Lieutenant Commander Data? Wow, people are on it.
Somebody is like ready to type.
Yeah, ready to roll. See if there are any other answers here. Yeah, the thing that kind of about the exoplanets, Tatooine, I'm interested to talk to you about this, Mike, because so the exoplanets in sci-fi oftentimes get portrayed as these single ecosystem planets, right? So Tatooine is a desert planet, and then there's like Hoth, that's an ice planet, and there's the magma planet, where the final battle between Anakin Skywalker and Obi-Wan takes place. And there's all these planets that basically are just a single biome. And I wonder how realistic that actually is. I mean, I know in our solar system, sure, there's the Earth, and you have ice at the poles, and you have tropics at the equator, and you've got various different biomes that are present within the Earth. So it's obviously not accurate here, but what about, do we know anything about any of the exoplanets? Do we have any idea on the conditions there, or even within the rest of our solar system? Are these, I guess the other objects are largely single biome.
Yeah, I think that's where this comes from. Before we knew about exoplanets, and we still don't know very much about the exoplanets. You look around our solar system and you see Mars, oh, that's the red planet. Venus, that's the cloudy one.
Right.
Saturn, that's the ringed one. Neptune is blue. And so I think in sci-fi, you sort of, the writers took these ideas from the planets that they, grew up seeing pictures of, and said, okay, let's just make this the desert planet, kind of like Mars is very deserty all over, except for its ice caps. But I think it's really something to think about really critically about why Earth has so many different biomes, and it has to do, I think, with its status as a habitable planet and the fact that life is playing a major role in reshaping our planetary surface environment. The reason why we have so many biomes is because life creates different biomes. There's not that much, like fundamentally different about like a savanna and a jungle, except that the jungle has like a lot of trees, right? And so, we see that life has increased the complexity of our planetary environment to a great degree. And maybe there's some kind of feedback loop there, where once you get life started, life will start to alter its environment in a way that creates a very complex environment and create new niches for life, to essentially new problems for life to solve and evolve into. And that gets back to the agnostic biosignature that I was talking about, that Stuart Bartlett was developing, where you're just looking at the complexity of a planetary surface over time and using that complexity as a proxy for whether or not there's life there.
That's super interesting. Yeah, I never really considered that. Yeah, so life modifies its environment to make it more appropriate for life, but also for different kinds of complex forms of life. Huh.
And there may be some underlying geological complexity that is, helping drive this too. So like volcanic regions, plate tectonics, things like this, oceans and land surfaces as well. So it's all interconnected. You really can't understand the history of life on Earth without understanding the history of geology on Earth. And the same is true in reverse. You can't understand our geological history of
without
this planet.
The presence of life.
Yeah, without the presence of life.
Huh.
So yeah.
Great food for thought there. Okay, sorry for putting that on hold. That the answer to that question that just occurred to me. So figured I had an expert. It'd be good to ask. I like this Saul the Man Tukolsky. Who did win the poker game? That's a good question. So the answer, of course, is Stephen Hawking, and here's a scene from that. But do you want to talk? Who won? Do you know who won the poker game? Who were all the members of the? It looks like Newton here, maybe.
Yeah,
or
Newton, Einstein, Stephen Hawking were playing poker against Data. And when they were interrupted by a call from the bridge, Stephen Hawking had just won a big pot of chips in the center against Einstein. And he famously said, or Einstein was saying, all the quantum fluctuations in the universe can't help your hand. And then Stephen Hawking says, wrong again, Albert. And shows his like 4 of a kind or whatever.
That's great. Yeah, so people are probably familiar with Stephen Hawking. I mean, he was a major kind of celebrity because of his, I don't know, because of his whole life story. He was a prominent astrophysicist. He wrote these very popular series of books. This is probably the most famous one. I read it when I was a kid, and it was very inspiring. Many of the audience members have probably read it as well. I'm assuming, have you read it, Mike?
Oh yeah, definitely.
Yeah, it's a good explanation. A good explanation of things. The thing he's probably most known for in the scientific community is the idea of Hawking radiation, which is a way in which that black holes can effectively evaporate over a long period of, over some period of time. It depends on their mass, but this is just kind of a diagram showing that. So you've got your black hole in the center. This is the warping of space-time towards it. And normally you think of black holes as just consuming everything as a massive object. Anything that gets close to them will orbit and eventually potentially plummet into them. And once it goes inside the event horizon, which is a set distance away from the black hole, it can't escape. Excuse me. And so the idea of Hawking radiation is just that it slowly evaporates because there's virtual particle pairs that are being created throughout the universe constantly at all these different places from the background energy, and the ones that are proximate to the event horizon, one might fall in and then the other one escapes, and so it slowly evaporates the black hole. But this is very dependent on the mass of the black hole. So microscopic black holes would evaporate very, very rapidly, but more macroscopic ones like a stellar mass black hole would take something like 10 to the 10 times the age of the universe or something like that to actually disappear and dissipate. But it's an interesting effect nonetheless. So thank you, Stephen, for that contribution. Okay, what else have we got here? What invention allows the transporter in Star Trek to record positions and momenta of every single particle in your body to reconstruct you exactly, potentially in a different location. So think about the transporter, think about its operation. I was always fascinated about that. What do you mean meta? Meta is what's doing that. That's a pretty good question, or a pretty good answer though. Yeah, I would. It's a cool technology. Teleportation has always been something that's really always fascinated me. It's kind of surprising that the Star Wars universe never really employed it. But the flux capacitor. Yeah.
This one's hard.
It is challenging.
Yeah.
Yeah, thinking about Star Wars and Star Trek, I'm a big fan of Star Wars, but in some ways my ideals more align with those of Star Trek. Simply, Star Wars, a lot of the people are born into those roles. Luke Skywalker is who he is because his father was Anakin Skywalker, right? And that's much more about this kind of like hereditary role. It's kind of like Harry Potter, right? Harry Potter was, at the beginning of book 1, he was just this kid who lived under the stairs with the Dursleys, and they didn't like him and he was a nobody. And then he found out that he was actually he was the boy who lived. He was the heir to this like huge hereditary history. And whereas Star Trek seems much more about a meritocracy, like you are what you are because of what you do, not because of what you inherited from your parents or from your grandparents or from your family or from your tribe or whatever. Mm-hmm. And I think my ideals much more aligned with that. It's just I feel like I was introduced to Star Wars and it played a major role in nostalgia-based stuff with me as a child, and so it resonates with me. But in terms of like, yeah, what it stands for, I'm much more a fan of Star Trek.
Oh, somebody got it. Somebody got it. Wow.
Somebody got it. The Horcrux.
Yeah, that's definitely it.
Yeah, it looks like somebody did get it. So the Heisenberg compensator. Do you want to talk at all about this?
Yeah, sure. So when the transporter was invented, it was actually invented to save money. They couldn't film, the shuttle pod going all the way down to the planet every single episode. So they invented this amazing thing called the transporter, which basically tears you apart subatomic particle by subatomic particle, turns you into energy, and then rematerializes you subatomic particle by subatomic particle somewhere else. And then when the technical consultants for the Star Trek: The Next Generation series, had to create their whole tech manual for the writers, they realized, wait a minute, how does this thing actually happen? Because they knew about this thing called Heisenberg's uncertainty principle, which says that you cannot know both the position and the momentum of a particle that is being heavily, described by quantum mechanics. And so because you can't know the exact position and the exact velocity of any molecule in your body, how are you going to basically record all that information and then reproduce that person exactly if you can't have that kind of information? So the technical consultants came up with a very sneaky solution to this and said that there's a component in the transporter called the Heisenberg compensator. And what does it do? It compensates for the Heisenberg uncertainty principle.
It breaks quantum mechanics to make it so this works.
Basically, yes. They should call it the quantum mechanic breaker instead of the Heisenberg compensator. But yeah, so I actually got to ask Mike Okuda, who wrote the tech manual for Star Trek: The Next Generation. I met him at a Star Trek convention once, and I asked him, so how exactly does the Heisenberg compensator work? And his response was, very well, thank you.
Oh, that's great. Nice. Well, I mean, it's cool though that they have a nod to the appropriate physics that would be relevant to these very complicated, sophisticated, futuristic problems. So even if they can't solve it, they at least invoke the appropriate branch of physics. So I appreciate that. Okay, how quickly did we're running out of time, but how quickly did the Millennium Falcon do the Kessel run? And I put quickly in quotes, because people probably know what this is all about. This is a reference to Star Wars, in case people were unaware. Han Solo, when encountered in the Mos Eisley Cantina by Obi-Wan Kenobi and Luke Skywalker, when they ask him about his ship, he boasts that the Millennium Falcon, his ship, did the Kessel run in this units, this distance in units or time in units. Extremely vary. Yeah, so people are largely getting this, and that is less than 12 parsecs. And really, this is kind of a it's become a bit of a joke. So initially in the film, so Han Solo says less than 12 parsecs, and to a person not aware of astronomy and its units, parsecs sounds like seconds, because it actually is a portmanteau of parallax seconds, and that sounds like a unit of time, but it's actually not. In the same way that a light year is not a unit of time, it is a unit of distance. Parallax seconds is not a unit of time, it is a unit of distance. So effectively, when asked how, the Millennium Falcon did the Kessel run in 10 miles, he was basically saying that, which doesn't really make a lot of sense. And so this kind of hung over the franchise for a long time. And then a few years ago, there was the release of this film, Solo, that was kind of on the backstory of Han Solo. And it kind of resolves part of this. So, oh yeah, this is an explanation of parallax. I'm not going to bother with parallax right now. But the idea is that, let's say you're trying to get from our position here to the Earth in the shortest amount of time. The standard thing is to travel all the way around here, so that you don't get close to the sun. This grid is basically just providing an idea of how warped space-time is. This is a product of general relativity. When you get close to massive objects like a sun or a star or a planet or a black hole, it warps the space-time around it, and it effectively makes the most efficient way of getting around it. There are different paths called geodesics, which describe different trajectories to get to something on the other side of it. And essentially, what you can do here is, or the way they corrected this in the Solo film to make this 12 parsecs make sense, was allowed, rather than the standard trajectory that kind of bypassed this warped space-time area around the star, the normal smuggler's route was to go 20 parsecs, kind of following my cursor. Can you see my cursor, Mike?
Yep.
Okay. But he was daring and flew closer to, this wasn't a star, it was actually a black hole in the film. He flew closer to the black hole and thus kind of like cut off some of the distance because he went into this warped space-time. And of course, it was more dangerous because he was traveling close to the black hole, but it allowed him to get there in a shorter distance because he was taking this short distance route through the warped space-time, and he did it in less than 12 parsecs. So it kind of cobbled together a solution that made sense based on this cryptic answer that was given in a film 40 years prior, which, I don't know, in some ways that's kind of cool. In others, it's like, whoa, you really put a lot of thought and effort into trying to like correct this, like debunk this kind of problematic line that was given a while ago. So it's, I don't know, it's cool. It's kind of cool. And it allows a better explanation of things like space-time and how space-time gets warped in the presence of massive objects, which I appreciate.
So ironically, wouldn't that take him longer because he would have that like time dilation?
There would be the time dilation. It's a balance, right? Because time dilation can be a minimal effect. If you get really, really close, then you get super, super time dilation effects. Like, I mean, if people are familiar with the movie Interstellar, there's a scene where some of the characters get very close to a supermassive black hole. I think it's supermassive. They call it gargantua anyway, so I assume it's supermassive, but I haven't seen it for a few years. And they get this massive time dilation effect where they experienced a couple of hours on the ship, but outside of that space, the time experienced was years. And that's a pretty extreme situation. Most of the time dilation effects that we experience in real life are very, very small. Even the difference between, traveling in the International Space Station for a year versus being on the Earth is like milliseconds for that year. So it's a very small effect. So I think in the end, it was balanced based on the shorter distance and this warping as opposed to the time dilation effect. Okay. In Star Trek, I think this is our last question. In Star Trek, the mysterious Verubin Nebula was named after which pioneering American astronomer whose work provided evidence for dark matter? Oh yeah, Zwicky, Vera, Rubin. Some good guesses. Zwicky's always a character. When did you begin at Caltech?
Me, 2012.
2012, okay.
Yeah.
So Fritz Zwicky was a scientist and faculty member at Caltech, but I think he passed away in the years preceding your arrival in the aughts.
Yeah.
But I've heard some crazy stories about Fritz Zwicky, that he was just this curmudgeonly, he was a genius and did amazing science, but this curmudgeonly old man.
Yeah, I've heard similar stories. Never had the pleasure or misfortune to have met him. Not really sure which one.
I heard that he'd do push-ups in the dining hall. He'd be just to keep up his fitness, and he did it in a very public way. And people are like, "What the heck? Why are you doing push-ups in the dining hall?" Okay, so it looks like people are generally settling on the answer of Vera Rubin. It's pictured here for her major contributions. She's mostly associated with the idea of, she and Zwicky as well are associated with the evidence for the presence of dark matter surrounding many massive objects in the universe, galaxies, clusters of galaxies, based on the fact that the motion of their constituents, stars and gas, is moving far too fast relative to what it should if you just count out the mass that's present from visible light. So there has to be some sort of unseen mass object or massive component. And there's a telescope that's being built in Chile right now called the Vera Rubin telescope that will be a real major contributor up there with James Webb and ALMA and some of these other major telescope facilities in terms of enabling our understanding of the universe. I'm pretty excited. Yeah, I didn't realize that they'd named this object after her in Star Trek. It's pretty cool.
And Vera Rubin worked at the Carnegie, what is now called the Earth and Planets Laboratory, where I work now. She's a big deal. She's passed away, unfortunately, but there are still tons of plaques on the walls of all of her honors, and even a huge sign right by an office that says Vera Rubin did her work here.
That's awesome.
Yeah.
Yeah, she was definitely a pioneer. It's exciting to see her honored in that capacity. Cool. Well, those are all the quiz questions. So good job, everyone, in your answers. It seems like people did a pretty solid job in getting most of them. Even somebody getting the Heisenberg compensator, which is impressive. So, yeah. Is there anything else you wanna talk about or say relative to science fiction? Do you have any other favorite science fiction kind of universes other than Star Trek or?
So everybody's been telling me to watch The Expanse. I haven't yet done so. So sorry. But I hear it's excellent and really good hard sci-fi. And I finished watching Lost in Space, the Netflix reboot, which I contributed to one line of dialogue in. It was the first time I was ever asked to be a science consultant for a major streaming series. So I have that is a soft spot in my heart. So yeah.
That's awesome. Yeah, I've been helping consult on a couple of upcoming projects, but I'm not supposed to talk about it because,
Yeah.
So hopefully those will come out and I can talk about it a little bit more, but
That'd be
stay
really
tuned.
fun. Yeah, I can't wait to hear.
They will be streamed. So anyway, well, thanks for being on the show, and thank you for your contributions. I really enjoyed your presentation and all of your commentary on stuff, Mike.
Yeah, of course. It's my pleasure.
Thanks, audience members, for sticking around. Sorry I didn't get to all the questions throughout. Happy to take more, and if people enjoy this sort of thing, maybe we can, obviously I left a lot of questions unanswered, at least with respect to the Star Wars universe. So if people are interested, by all means, we could try and do something similar. I know a lot of people who are really knowledgeable about other aspects of this science fiction universes. There's a lot of Doctor Who fans who wanted to contribute some capacity. I know my boss does. So if there's interest from people, let us know, and we can try and cover a particular thing. Or if you think this is just rubbish and we should go back to doing our standard, just talk about science and not necessarily tie in with science fiction or popular media, let us know in the comments as well. So thanks for joining us on your Monday nights, presumably, or maybe Tuesday morning, depending on where you are. And yeah, our next event again, June 3rd will be a stargazing lecture that I'll post very shortly. That's all about studying the interiors of Jupiter and Saturn using basically seismic activity, or the equivalent thereof, of acoustic waves traveling through the upper atmospheres of Jupiter and Saturn, so we can learn about their interiors, given by Dr. Janos Dewberry. And then we'll do an Astronomy on Tap, or a couple, in the next month or so. There's going to be the American Astronomical Society meeting that is here in Pasadena, where there will be a lot of astronomers present, and I'm trying to rope some of them in to do it. And I'm also trying to do it in person, but I don't know if that's going to happen because it's a big hassle. Anyway, stay tuned. There will be more science to be had. So thanks everybody for sticking around, and I'll see you guys next month.